Okay, so this is the second part to the problem that we're working on. And we did part A, so this is going to be part B. And part B wants the maximum positive shear at C. So I have to pretty much start all over. So what I'll do first is I'll draw the structure, and then we'll imagine this magical shearless connector at C. Right? I still have my roller at B and my pin connection at A. And then what we're going to do, well, we're going to come along and we're going to apply positive shear to both segments. And how will that move? Well, if we look on the right side, me pushing it up, it's going to go up, right? If you go look at this left piece, if I push down the side, it's just like a seesaw. It's going to go down, seesaw over A, and this end is going to go up in the air. So there's the shape, the qualitative shape of my influence line. So let's transfer that down onto a plot of the shear at C. And let's see, I've got this point, this point, this point. Those are all 10 feet. And if I transfer my line, I get something like that. And just to emphasize it, I'll come here and put in the values. Now the great thing about shear is we don't have to draw any free body diagrams. We know that the change in shear at this transition point is 1. And you can see that on the right side it's 10 feet, on the left side it's 10 feet. So each of these respective heights are going to be equal. So that means that this is going to be 1/2 and this is going to be -1/2. And now what's this value going to be? Well, 10 is to 1/2 as 10 is to 1/2. And there, done. And this doesn't have any unit. These are dimensionless values. Now that would have taken you 10 or 15 minutes to do the old technique. So you may not be a big fan of Mueller-Breslau right now because you're still maybe trying to sort it out. But as your diffuse brain works on it for the next couple days, you're going to like this. This is going to be good. This is going to be good. So now I can just solve the problem. So the problem says, what's the maximum positive shear at C? So we'll start with the concentrated load. And the concentrated load for this problem is 20 kips. And what is the largest positive value in the influence line? 1/2. So it looks like that's going to contribute 10 kips. Now where could that position be? It could be here at the free end or all the way over just to the right of C. Just to the left of C, it creates a negative value, so we don't want that. So actually there's 2 possible positions for that live load to be to create the maximum shear at C. So what about the uniform dead load? We've talked about before, dead load goes the whole structure. You don't get to choose. So we have to multiply the dead load intensity, which is 300 pounds per foot, by the total area under this curve. So I'll start with the 300 pound per foot intensity. I've got 3 triangles I have to deal with. So I'll go ahead and put the 1/2 on the outside. 1/2 base times height. And I'm just going to work my way from left to right. So starting here has a base of 10 and a height of 1/2. Then I come here. That's a base of 10 and a height of minus 1/2. And then the third one is a base of 10 and a height of positive 1/2. Now this is kind of pretty easy. This one and this one cancel out. So I'm just left with 5 times 150. What's that, 650? That's 750. 750 pounds. So this is going to be, I'll move it into kips, so it's going to be 0.75 kips. Okay? So now, let's look at the uniform live load.
Wouldn't it be 2 feet?
Did I do something wrong?
Uniform dead load would be 2 feet.
No, the shear is just kips.
Oh, okay.
See, so you just have a unit of feet here. You got pounds per foot. The feet cancel. You just left with pounds. I got 750 pounds. I converted it to kips. So now with the uniform live load, we can start and stop it and do what we want. And you can see in this particular drawing, since we're looking for positive, there's 2 sections that are positive. The first 10 feet and the last 10 feet. So we're going to consider both of those. So we're going to take our 600 pound per foot intensity. And again, there's 2 triangles, so I'll make it half. And the first one, base of 10, height of 1/2. And the second one has a base of 10 and a height of 1/2. So if you calculate that, you get 10, 5 times 600, you get 3,000, so that becomes 3 kips. So you put that all together, you get shear at C max positive. You'll just add these up. 10 plus 3 plus 0.75 is 13.75 kips. Now I've got a little more space here, so I want to kind of show you what this looks like. So let me redraw the beam with my roller at B and my pin at A. And we'll start with the dead load. So I'll put a blue line underneath that, and I just wanted to show you that the dead load runs the entire length of the beam. Let's do the uniform load, which is going to be the 3 kip contribution. Well, it's going to run just the positive parts of the beam. So it will run here to here and here to here. See that? And then now we've got the positive. So this could be either here or here. There's 2 conditions. I'll just draw it here. It also could be here. Either position will produce the... I don't know how to do that without confusing you. Maybe I'll just draw it in one position. That's correct. So I just wanted to show you what the combined loading looks like that produces that shear at C. Okay, any questions about that one? Let's work some more.